welcome to this explainer. Today, we're diving into a literal masterclass on the ultimate testing ground for finding extraterrestrial life and the absolutely monumental engineering required to actually get us there. We are talking about the Jovian Frontier, Jupiter and its incredibly diverse moons. If you really want to understand what the future of deep space exploration looks like, well, this is it. This is the frontier where humanity's most ambitious science meets its most brutal environmental challenges.
We've got a packed syllabus today. We'll be hitting Jupiter as a mini-solar system, the hunt for extraterrestrial life, engineering for extreme environments, and finally, tomorrow's deep space technology. So, are we alone in the universe? I mean, it's pretty much the most profound question we've ever asked as a species, right? And trying to answer it isn't just sci-fi anymore. It's actually the primary scientific driver behind venturing into the massive Jovian system. Every risk we take, every dollar we spend, every decade of development poured into exploring Jupiter is ultimately chasing the answer to this one fundamental question. Okay, let's dive right into Section 1, Jupiter, a mini-solar system. To really grasp why we're so obsessed with going out there, we have to look at what Jupiter actually is. With more than 90 known moons, a gigantic magnetic field, and crazy radiation belts, the Jovian system isn't just a planet, it acts as the perfect natural laboratory. It's quite literally a mini-solar system right in our own backyard.
You might be wondering, with all the places in space we could explore, why this specific gas giant? Well, it's because giant planets are basically the most common type of exoplanet we're discovering around other stars across the galaxy, so Jupiter essentially serves as our local, accessible template. By studying how Jupiter evolved and how it gathered all its massive bulk early in our solar system's history, we get a direct model for understanding how giant planets, yeah, even those scorching hot Jupiters orbiting super close to their stars, form everywhere else in the universe. But before we even get to the moons, we have to talk about the planet's frankly insane atmosphere. We're talking the Great Red Spot, supersonic winds, giant storms, massive lightning systems, and incredibly dense ammonia clouds. I mean, it makes our absolute worst hurricanes on Earth look like a gentle spring breeze. And here's the cool part. Future deep-diving probes will actually descend straight into that chaos. By directly measuring the extreme pressure, temperature, and chemical composition as they plunge into the depths, we can decode the universal atmospheric physics that govern gas giants everywhere.
Right, moving on to Section 2, the hunt for extraterrestrial life. This is the real prize of our study guide, and the ultimate target for astrobiologists. We're shifting away from the turbulent atmosphere of Jupiter and looking at the icy, silent ocean worlds of Europa, Ganymede, and Callisto. Because these moons might just harbor the biological secrets we've been searching for.
Let's look at the timeline of how we're approaching this. NASA's Juno mission has really been doing the heavy lifting, preparing the way by analyzing deep atmospheric structures and wild polar cyclones, proving that Jupiter is far more dynamic than we ever imagined. Juno laid the vital groundwork. But near-future missions like the Europa Clipper are shifting the focus entirely. Clipper is going to directly target the environment suitable for life, performing incredibly detailed studies of Europa's ice shell and that dark, hidden ocean beneath it.
So, the absolutely crucial question is, why is Europa considered the top target for discovering extraterrestrial life? Well, the evidence points to a global subsurface ocean that literally holds more liquid water than all of Earth's oceans combined. Think about that for a second. Because it has internal heat sources and chemical nutrients mixing around, scientists are hunting for very specific chemical and biological signatures, organic molecules, and potentially even microbial ecosystems. A confirmed discovery here would be, without a doubt, one of the greatest scientific achievements in human history.
Okay, Section 3, Engineering for Extreme Environments. Now, what's really interesting as we pivot here is that talking about finding life sounds amazing, but to actually pull it off, spacecraft have to survive a truly brutal environmental gauntlet. Let's dig into the sheer engineering required to operate in one of the most hostile regions of space.
First massive hurdle, the sheer distance. Jupiter sits at an extreme average distance of nearly 800 million kilometers from the Sun. You definitely don't just point a rock in a straight line and hit the gas. Navigating this immense distance requires massive fuel reserves and complex planetary gravity assists. We are talking about a travel time of anywhere from 5 to 8 years just to arrive at the destination.
And when you finally do arrive, the environmental extremes are just staggering. Temperatures out there plunge to a crippling minus 150 degrees Celsius. Landing systems have to be engineered to reliably navigate vacuum-exposed, ice-covered surfaces and completely unknown terrains, all while surviving this absolute deep freeze. Now, what if something goes wrong?
You can't just pick up a controller and course correct. Because of the vast distance back to Earth, we're dealing with a round-trip communication delay of 30 to 50 minutes. Imagine trying to play a video game, but every time you press a button, it takes nearly an hour for your character to actually move. This massive lag prevents any real-time human control. It introduces severe technical hurdles, meaning our remote robotic operations have to be entirely self-reliant.
Then you've got the power problem. Thanks to a little thing called the inverse square law, solar energy gets exponentially weaker the farther out you go. Out of Jupiter's orbital distance, solar panels receive only a tiny fraction of the sunlight they'd get near Earth. This week's sunlight dictates heavy power limitations, forcing our engineers to design much larger solar arrays, utilize radioisotope power systems, or even develop advanced nuclear reactors just to keep these long-duration missions alive. But honestly, the absolute deadliest part of this entire gauntlet? Jupiter's magnetic field. It's the strongest planetary magnetic field in the solar system, and the radiation belts near moons like Europa are so intense they will literally destroy conventional electronics within days. To survive, spacecraft require incredibly heavy shielding and highly specialized radiation-hardening techniques. Every single processor must be radiation-hardened, and the systems must be perfectly fault-tolerant just to keep the computer brains from being completely scrambled by the radiation.
Which brings us to Section 4, tomorrow's deep space technology. To conquer these immense challenges, the cold, the distance, the radiation, the ice, we have to look way beyond today's engineering. We need a completely new arsenal of futuristic, advanced technological solutions.
So, if we want to test Europa's oceans for life, we've got to get through that ice. Enter the cryobot. These are advanced robotic machines mechanically designed to literally melt and drill their way through thick, rock-hard planetary ice shells. Once a cryobot finally bypasses that massive frozen barrier, it can deploy autonomous underwater vehicles directly into the dark, alien depths below. And actually get these heavy, complex robots out to Jupiter faster and keep them powered up, we need a deep space arsenal. We're looking at long-duration nuclear-powered orbiters, advanced radiation shielding, and revolutionary propulsion like nuclear electric and, yeah, even fusion propulsion. We are talking about fusion drives, peak sci-fi turning into reality. By harnessing nuclear and fusion tech, we can completely revolutionize outer solar system travel, solving those massive power limitations and dramatically cutting down those agonizing 5 to 8 year travel equations. But remember that 50-minute communication delay we talked about? We solved that through artificial intelligence. Future missions are going to utilize autonomous swarms, multiple coordinated robotic explorers, maybe even mini submarines in Europa's ocean, working alongside AI-driven exploration systems. These AI systems will make their own scientific decisions, identifying microbial life or navigating super hazardous underwater terrain completely autonomously, without waiting for someone back on Earth to pull the levers.
As we wrap up this explainer, we really have to look at the ultimate high-stakes balance of the Jovian Frontier. Think of this as your cheat sheet. On one side, we have the greatest possibilities in science, searching for life, exploring hidden ocean worlds, and understanding giant planet formation. But on the exact flip side, we have the immense challenges trying to stop us: extreme distances, intense radiation, crippling temperatures, and of course, massive costs. It is the ultimate scientific tightrope walk.
I want to leave you with this final thought to ponder. The hurdles to reach the Jovian system are absolutely colossal. But if human ingenuity can actually overcome them, if our spacecraft can survive the blinding radiation, the freezing vacuum, and that vast distance from the sun, what exactly are we going to find swimming in the dark, hidden oceans of Europa? Conquering these hurdles might just lead us to the greatest scientific discovery in human history. Thank you so much for joining me for this explainer. Keep asking those big questions, and I'll catch you next time.